Look up at the night sky. What do you see? Stars, planets, galaxies. A breathtaking cosmic ballet. But what if I told you that everything we can see, everything we've ever observed, makes up less than 5% of the entire universe? That's right. The other 95% is a complete mystery. A cosmic ghost story wrapped in the fabric of space and time. This is the story of dark matter and dark energy. Let's start with dark matter. Back in the 1930s, an astronomer named Fritz Zwicky was studying the Coma cluster of galaxies. He noticed something strange. The galaxies were moving so fast that they should have flown apart. The gravity from all the visible matter, the stars and gas, just wasn't strong enough to hold them together. It was as if some invisible mass, some dark matter, was providing the extra gravitational glue. For decades, this idea was on the fringes of science. But then, in the 1970s, an astronomer named Vera Rubin confirmed Zwicky's suspicions. She was studying the rotation of individual galaxies, like our own Milky Way. According to our understanding of gravity, stars farther from the galactic center should move slower, just like the outer planets in our solar system orbit the sun more slowly than the inner ones. But that's not what she found. Instead, the stars on the outer edges were moving just as fast as the ones closer to the center. This was a bombshell. The only way to explain this was if the galaxy was embedded in a massive, invisible halo of, you guessed it, dark matter. Her observations were so precise, so undeniable, that the scientific community had to take notice. It became clear that this wasn't a fluke. It was a fundamental feature of our universe. So, what is this stuff? Well, that's the billion-dollar question. We know what it's asterisk, not asterisk. It's not just dark clouds of normal matter, because we would be able to detect them in other ways. It's not antimatter, because we'd see unique gamma rays when it annihilates with normal matter. It's not a bunch of black holes, as we haven't seen nearly enough gravitational lensing events to account for it. Scientists call it dark, because it doesn't seem to interact with light or any other form of electromagnetic radiation. It doesn't shine, it doesn't reflect, it doesn't block light. It's completely transparent. Its presence is only felt through its gravitational pull on the things we asterisk. Can asterisks see? Imagine trying to describe an elephant to someone who can only feel its footsteps. That's the challenge we face with dark matter. The leading candidates for what dark matter could be are hypothetical particles. The fruit runners are called WIMPs, which stands for weakly interacting massive particles. These are particles that, as the name suggests, are heavy and only interact through gravity and the weak nuclear force. This would explain why they're so hard to detect. To find them, scientists have built some of the most sensitive experiments ever conceived. They've gone deep underground in old mines to shield their detectors from cosmic rays. They're using massive vats of supercooled liquid xenon, hoping that a WIMP will occasionally bump into a xenon nucleus, creating a tiny flash of light. It's like listening for a single pin drop in the middle of a rock concert. So far, we've found nothing definitive, but the search continues. Now, hold on, because the story gets even stranger. If 27% of the universe is dark matter, what about the other 68%? This brings us to an even more enigmatic force. Dark energy. Our understanding of the universe's fate took a wild turn in 1998. Two independent teams of astronomers were studying distant supernovae, which are powerful stellar explosions that act as standard candles for measuring cosmic distances. They were trying to measure how much the expansion of the universe was slowing down due to gravity. Everyone expected the expansion to be deceptive. Gravity, after all, pulls things together. Think about it. If you throw a ball in the air, gravity slows it down, stops it, and pulls it back. The universe should be doing the same, but the results were shocking. The expansion of the universe isn't slowing down at all. It's accelerating. It's speeding up. It's as if you threw a ball in the air, and instead of coming back down, it shot off into the sky faster and faster. Something is pushing the universe apart, counteracting gravity on the largest scales. Scientists named this mysterious repulsive force dark energy. So what is dark energy? The honest answer is, we have absolutely no idea. It is, without a doubt, the biggest mystery in all of science. One idea is that it could be a property of space itself. Even in a perfect vacuum, what we think of as empty space, quantum mechanics suggests there's a seething froth of virtual particles popping in and out of existence. This could create a sort of vacuum energy that pushes space apart. The problem is, when physicists try to calculate how much this vacuum energy should be, the number they get is astronomically, ridiculously, mind-bogglingly large. It's 10 to the power of 120 times larger than what we observe. This is often called the worst theoretical prediction in the history of physics. It means our fundamental understanding of physics is profoundly incomplete. Another idea is that dark energy is a new kind of energy field, something like an electric or magnetic field, but that permeates all of space. This field has been nicknamed quintessence. Unlike vacuum energy, its strength could change over time, which might explain why it only started dominating the universe in the last few billion years. The existence of dark matter and dark energy forces us to reconsider our place in the cosmos. The universe isn't just the collection of stars and galaxies we see. It's dominated by two invisible components that we are only just beginning to comprehend. One is pulling everything together into cosmic webs, and the other is pushing everything apart at an ever-increasing rate. This cosmic tug-of-war will determine the ultimate fate of our universe. Will dark energy continue to dominate, pushing galaxies so far apart that future observers will want to be able to see any galaxies beyond their own, leaving them in a cold, dark, and lonely universe? Or could its properties change? We just don't know. But this is what makes science so exciting. These aren't just abstract problems. They are clues to a deeper reality. Finding the true nature of dark matter and dark energy would revolutionize physics, cosmology, and our entire perception of existence. We live in a truly remarkable time, standing at the edge of a vast, dark, cosmic ocean, just beginning to dip our toes in. The greatest discoveries are still ahead of us. Thank you so much for joining me on this journey into the unknown. If you've found this as fascinating as I do, please hit that like button and consider subscribing for more adventures into the mysteries of our universe. Let me know in the comments what you think dark matter and dark energy might be. See you next time.